All right, so we're talking about total internal refraction or just refraction in general for now. So what's the idea behind refraction? What's physically happening? Who can explain that real quick? What's physically, it's a simple explanation of what's happening. The math could be a little complicated. But what's actually happening?
Like it bounces off a certain surface.
Yeah, it either bounces and it's reflected, or it bends the light and it's refracted. So it either gets bounced off the surface, and that's reflection, or it gets refracted and the light simply gets bent as it goes through that medium. Now, depending on the medium itself and its index of refraction, n is called the index of refraction. Based on that value, the light either bends away from the normal or toward the normal. The normal, if you remember, is a perpendicular line. So let's go ahead and draw this so we can see what's physically happening. So let's say that this first medium has a given n value of 1.7, and the second medium has a given n value of 1.1. Take a look at this and think to yourself first, what's physically happening? This light ray comes through here, it hits the normal right here, here's the normal. All right, that's called the normal right there. It's a perpendicular line to the surface. Does this ray get bent toward the normal or away from it? Well, we have to first know what our angle is to start. Let's say our angle to start is 25 degrees. The question really that's posed is, the angle coming out, is it going to be more or less than 25? And then eventually, if that angle it turns out to be greater than 90, you have total internal reflection. Okay? Even though it is a means of refraction, it's total internal reflection. So we can see what happens here, and let's try and figure this out. What law could we use? What law could we use? Look at your formula sheet. It's on there. Under refraction, or Snell's law is the name. Look for a formula over there. Along the right side of your formula sheet. What do you got, Katie? Go ahead. And r, sine theta r. Whenever you see a subscript, just say it successively after, like you'd say H2O. So Ni sine theta I equals Nr sine theta r, which is Snell's law. Snell's law tells us that the index of refraction and the angle, the product of those two things, now the angle obviously is the sine of that angle, is a consistent factor. This is like the continuity equation. Remember the continuity equation was like, well, the area decreases, but the velocity increases. It's the same thing that's happening here. If the n value goes from 1.7 starting to 1.1, isn't that decreasing? Take a look up. If the n value goes from 1.7, where it comes in the incident medium, the top one, into the refracted medium, which is 1.1, if n goes down, theta, or sine theta, the overall value, has to go up for this to be equivalent. So if this angle here is 25, there's a good chance this is going to be greater than 25, right? So this is going to most likely bend away from the normal. You could remember this also. We talked about memorizing this, and we talked about when it bends away and toward the normal. You could think about it that way. Remember that air is the fastest traveling medium, or a vacuum really, and that n value is 1. Okay, so this is going to definitely bend outward. It's not going to follow this dashed line that it should have followed if this medium was the same. Right? It would have traveled along that dashed line had it not been bent. But it's going to be bent such that this angle here is definitely going to be greater than 25 degrees. I know it's going to be greater than 25 because, again, n goes down, sine of theta r has to go up. And now that you know your trig functions, I could actually do this. I couldn't do this earlier in the year. Sine of 0, we start here, is 0. Sine of 90 is 1. The sine function increases from 0 to 90 degrees. So for this whole function to increase, theta just has to get greater than 25. Well, let's figure out what it is. So Ni is the medium that it starts in, the incident medium, so that's Ni up there. And R is the medium it's being refracted in. So we start by putting those in place. Then we recognize over here, this is the angle of 25 degrees. This is the incident angle, the angle it comes in at. So that goes here. And then finally over here, our goal is to find theta r. Our goal is to find theta r. You could solve this analytically, but I find that some students get a little bit inundated with the sine functions and they kind of get confused by it. So if you like, it might be easier to just actually type these numbers in, divide by 1.1, and get yourself a number on the left-hand side. Get yourself a decimal. So again, get sine theta r by itself by multiplying these two and then dividing by this guy right here. Because then you have sine inverse of sine, and I feel like a lot of students get really stumped with that. I think it's a safe bet to say that this might be a section where you want to plug in the numbers earlier, and then later on, we'll take the sine inverse to get theta r by itself. What do we get for that number? 0.65? Give me 4 decimals just for this, because sine it's very sensitive, the functions. All right. And the reason I say 4, by the way, this is a fun fact. Mr. Hall probably talked about this, because I feel like he would. I just know him well. In high school, we didn't have, the graphing calculators weren't around. So you guys press sine 20 and you get a number? That never happened. You didn't have a calculator. So in the back of your textbook, you have what was called a sine table. And you look up like the sine of 20 and it'll give you 4 decimal spots. And then later on, we have to start figuring out how to get theta. Well, to get theta, don't you guys press second sine of this number? Well, we don't have a calculator then either. So you had what was called an inverse sine function table or inverse cosine function table. And it would be all these decimals. And you'd have to find out which your decimal looks closest to. So you look in the table for 0.6531. It was never there. They had 0.6530 and 0.6535. And then 0.6540 and 0.6545. Every single thing would go up by 5 here. And you'd have to interpolate the answer. This would give you a decimal, a degree, and the next one would give you a degree, and you'd say, all right, mine's between 0.6530 and 0.6535, so it's between these two angles, and you'd estimate what was between those two. That's how you got your angle. So that's why you always traditionally use 4 decimals for any sine or trig function. So what do you get for theta r? Make sure you're in degree mode, please. I didn't ask for verification, but was Zoe right, by the way?
Yes.
Okay, good. What do you got?
40.8.
And we knew that this had to be greater than 25 degrees. That was the statement we made in the beginning. The sine function had to go up because the n value went down. If you want to jot that down, you can. If the index of refraction goes down, the angle goes up. How are they related? Indirectly or inversely. Very good. Indirectly or inversely related. Now, let me go one step further, okay? You can have total internal reflection, which is when the media or the ray bounces back into the first medium, when the angle of theta r is 90 or more. So if you do a problem on the test and this answer comes out to be more than 90, here's what it means. Look back up at the diagram real quick. More than 90 would be an angle, look, there's theta r right there. So this is currently 40.8. It's not drawn to scale, obviously. I know this is greater than 45 by looking at it. But assume this is 40.8, okay? This is 90 degrees up to here. So if the angle is greater than 90, it means you're back over here. That means the ray is doing this. It's being internally reflected. So when theta r is greater than 90, this ray gets bounced back in. This is the angle greater than 90. That angle is clearly, that's an ugly way to draw that angle. This angle is greater than 90 right here. Okay, 90 would be actually on or along the surface interface between the two media. It would be right along the surface, that's 90. Greater than 90 means that it's bending beyond 90 and back into the actual material. All right. We kind of knocked out like 3 birds with 1 stone right there. Bird number 1, multiple choice, understanding the relationship between n and theta. As n goes up, theta goes down. You did this in the lab. It was actually at the very end you made some conclusions about relationships between the variables and parameters. If n goes up, theta goes down. Second conclusion, or second bird we killed with this, for a short answer kind of question, if you have to explain what total internal reflection is, we just went over it. We said, well, what happens is the light ray gets bent, so theta r is more than 90 and it bends back in. That's exactly what it is. Okay? That's the phenomena of fiber optic cables carrying those signals. Third, we looked at a math problem of what you could expect for something that would involve Snell's law. Okay? What else? Another topic. Yeah? Simple harmonic motion? Okay. So for simple harmonic motion, it depends on if we have a pendulum system or a mass spring system, but they're analogous. So we'll take a look at let's look at the spring scenario, and then we'll talk about how the pendulum would work also. So let's say we've got a spring with a K value of 200 newtons per centimeters. That's the K value of the spring. And let's see. It's stretched. Well, no, let's say a force is applied, a weight is applied, Fg, suspended. A weight is hanging from the spring, and the weight hanging from that spring is 2 kilograms. Sorry, that should be the mass, rather. The mass hanging from that spring is 2 kilograms. We want to determine how far it'll be stretched, right? How far it'll be stretched, and the period of oscillations if it starts to vibrate harmonically, if it goes up and down with the same amplitude. So those two things. Which one's easier to start with, I think? Find either A, how far it's stretched, or B, the period of oscillations. Which is easier to find? Theo? Why, Theo? You're right. Why? Yeah, period equals 2 pi root m over k. You're given both of those things, so start with that one. Even though it's part B, or I ask you the other way maybe, most likely on the test I'll guide you through the problem like you'd have to do part A first. Okay, but I want you to actually sometimes when you're doing it here understand why you would choose one over the other. Now, if you had to find the displacement x, how far the spring is stretched, what do you have to do that? You can't use the given information, you need more. How do you find the stretch length of a spring? X. The stretch length of a spring, X. How do you find it? What's the formula? Emma? Yeah. Fs, the force in the spring, equals negative Kx. Hooke's law. And to do that, we need the force in the spring. Well, we have a mass. We have to convert that to a weight, and then we'll know the force in the spring. So there's one extra step there. Now, for both of these scenarios, what do I have to do first? For both Hooke's law and to find the period. What do I have to do first? Not kilograms. Kilograms are good. Those are a base unit of mass. It's the one that's the exception, remember? Most things are regular, but kilograms is actually... To what? Yeah, centimeters should be written in meters to start. So we need to get rid of centimeters. Where are they currently? Where's the unit centimeter? In the bottom, right? So how do I get rid of it, Joe?
Well, you can just multiply on the other side so it cancels.
So I put it in the top, right? So I can cancel it. What goes in the bottom? What am I trying to get to? What's the basic unit for length? Not centimeter, just meters. How many centimeters are in a meter? This is stuff that at this point in the year you should know. 100. Centi means 100, right? Or 100th, rather. Okay? 100 centimeters in 1 meter. So that's my conversion factor right there, canceling centimeters. And now I have 200 times 100, I'm going to have 1, 2, 3, 4 zeros. 20,000 newtons per meter. So we've got a spring that is extremely strong. It's got a large amount of newtons necessary to stretch it a meter. Well, a meter's pretty far. This is a meter. Stretching a spring this far should take a lot of force, But to do that, clearly, it's a lot of force here, 20,000 newtons. So we go ahead and we can calculate the period of oscillations here. Okay, we can find out what the period of oscillations would be if this were set in simple harmonic motion. It's going to be a very what? Small or large answer? Don't do it, just figure it out. Why?
Because K is a very large value.
K is a large value, and where is it going to go, Ann? In the... K goes in the denominator, right? Which is what makes the period itself a very low number mathematically. Physically, you can think about it too. If it's really strong, the spring is not going to oscillate for a while. It's going to be like this, real quick, the oscillations. So because a large number is going in the denominator, okay? And then 2 will go in the numerator. So we'll get a very low number. Now, it doesn't matter what the number is for now. Let's take a look at the second part where we're trying to find out how much displacement there would be. So the mass is 2 kilograms. Let's make a new spring because that K value is going to be, actually we'll use it, whatever. It's just going to be a very, very small answer. The mass is 2 kilograms and it's hanging from the spring. So let's draw a scenario. As the ceiling, a spring with a mass on the end. That's what's happening here. The free length of the spring is whatever it is. I don't care. I asked, find out how much it's stretched. That's what X is. The formula is this. But we don't have a force right now. Fs is where on the diagram? If I were to draw a free body diagram of this mass, what does Fs look like? Is it an arrow going up, down, left, or right? Force in the spring. Think logically. You don't have to memorize stuff, guys. A weight is pulling down. A weight is pulling down. Up. The spring has to pull up. Well, again, what's pulling down in this case is a mass's weight. Not the mass itself. I mean, it is technically, right? But it's the weight of the mass that's really pulling. A pull is a force. So when I say it's pulling, you have to say the weight, not the mass, really. Mass is a mass. So the actual weight, but we don't have the weight. But we can find the weight always. The weight of an object equals the mass times gravity, always. This is the simplest thing you've done all year. Okay, finding weight of an object. mg. You've done it so many times now. So 19.62 is the weight, and that weight is pulling downward. The spring force is then positive 19.62. Again, this is the value I got. If I were to actually label it there, I would label it as negative 19.62 because it's pulling down. The spring is pulling back up. And this equals negative 20,000 times x. Well, x, its value is going to be negative. That's fine. It just means the spring is being stretched which way? Down, which is the answer of what's happening here. Okay? X will be a very, very small number. 19.62 over 20,000. And again, it will be negative. It will be negative. Got it? Negative 9.81 times 10 to the negative fourth. Which makes sense that we get 9.81 because we multiplied by 2 earlier, didn't we? Didn't we multiply 9.81 by 2? And aren't we now kind of dividing by 2 if you think about it? And all these negative 4 comes from all those zeros, 4 zeros. Okay, it's a very small number. The stretch would be minuscule. This would be, actually this is great that we did this example because I'd love to always make you see applications of this. So this would be a great example in the assembly today. You saw the girls made that like model suspension bridge. A real suspension bridge would have cables with K values beyond this, way beyond 20,000. Strong enough so that there's literally almost no stretch. But there's actually supposed to be some sort of give in these cables. They're not supposed to be all completely taut. They're supposed to have a little bit of room for wiggle. So in case there is some sort of a catastrophe, it can actually rebound itself or like compensate for that vibration that may occur. All right, good. Hooke's law and harmonic motion. What else? Again, we talked about a lot there. All that stuff. Multiple choice, short answer, and then we did a math problem. So it's good that we're doing math problems, but we'll keep talking about the theories behind them every time. What else was something you may have struggled with? By the way, the other class already did a day of this yesterday, so their video's online. So they asked different topics than you. So if you want to just do extra studying, before, it's not till next Thursday. So if it's like next week on Tuesday or Wednesday you want to watch videos, watch the other sections videos from day 3 on. Day 1 and day 2, we did formula sheet for both classes.
What are we doing wrong?
For the double, you mean?
Yeah.
I don't know. I haven't decided. Maybe what I'll do is the first period we'll do this, and the second period we could watch it honestly, but I feel like you guys should review. I don't know. I mean, it's your call. What I can do is this: I can come up with some sample problems maybe, or have you work on some sample problems if you want to practice on your own. And if people want to watch October Sky, they can watch all those practice problems. You can just put headphones in and listen to music and practice problems if you want. But I don't want it to make it not conducive for studying because it is final review. I did that in the other class. They were fine with it. About 5 people were studying and doing problems, and others wanted to just watch a movie and relax.
In the equations, E equals FE over Q, and also E equals KCQ over R squared. What's E for?
Yeah.
What's it solving for?
What was what?
E, what's it solving for?
The electric field intensity. Electric field intensity. Its units, if I recall, were newtons per meter, or newtons per coulomb. Because it's the same formula as Fe, KQ1, Q2 over R squared, except it's missing a Q, isn't it? So it's missing a coulomb. Q is coulomb. So it's newtons per coulomb. It's called electric field intensity. And it's pretty much the strength of the electric field, but it's not the force exerted on the particle, but the strength of the field.
Then what would the unit for FE?
Newtons per coulomb. Newtons per
Is
coulomb.
this chapter 17?
Chapter 17, Ed?
Yeah.
Yeah, the units for E equals KCQ over R squared are newtons per coulomb. That was electric field strength produced by a source. Q is the source. Jot that down. Q is the source, not a particle. Q is the source. The source creates an electric field around it, and your goal was to measure the strength of the field. If it was a positive source, the field was drawn away, because we think about a positive test charge somewhere. If it was a negative source, that positive test charge would be pulled toward the source. We drew the arrows toward the source. What else? What else? What else?
Well, just read in chapter 14.
Mm-hmm.
The formulas.
What was name a topic in it? I don't remember the numbers.
Well, I know, just like looking at this, because they have the there's practice problem, we can formulas, so it goes going back to.
No, there was no math on this section. Yeah. We went on to look at like fraction, like that's what math is about. But not in the previous one. It's the only section with no formulas. And there actually is math we could have done in that section, but I think I cut it out. There was part that we could have done a little bit of math, but I think I removed it or just didn't cover it. What else? Come on. You should be looking at the final exam sheet. Your notes, Emma. Perfect. What do you got? Something with work? Mechanical work? Like in the beginning of the year or electrical work at the end of the year? Beginning. By the way, congrats. That's an awesome award to win. That's an achievement. I was like, oh, so I hear Natalie gets 25. So and 2 tied. I'm waiting for 26. Everybody, right? It was so overclimactic. It was unbelievable. 61? It's incredible. Well, do you have a commute in the morning and going home? The commute is the big part too. Do you read on the commute every day? Yeah, I'm the same. I read every day on the commute and I love it. It's the best. I read a book in a week and a half recently the other day. Just because every day on the commute, it's an hour and 20-minute commute round trip.
Emma's week and a half.
Yeah, you read more than a book a week by doing it that way because it's 52 weeks in a year.
I read a lot over the break, so sometimes
A book in 4 days, right? Yeah. That's the best. I remember my favorite ever. My favorite story to read has been I don't know if you've ever read this book, Alexander Dumas, The Count of Monte Cristo. It was a book I read in high school. And the reason it's one of my favorite books, and this is weird, was I was on a trip and there was an 8-hour bus ride. And I talk with a lot of other people and stuff, but after an hour, what happens on bus rides? Everybody goes to sleep or watches a movie, right? So I sat there and read the whole book, and I didn't put it down the whole ride because it was that good. It was like 400 or 500 pages. And it was the first time I'd ever read like a full-length book in one sitting. And it was incredible. But that feeling of being, oh man, so nice. But I just finished a book series the other day and I'm so sad. So sad. I've been reading it for 2 years and now I'm like, it's like every day I look forward to it on the subway. I'd be like, oh, all right, what's going to happen this time? It's been a lot, like 15,000 pages of books. 15 books, and I'm like at the point where I'm like, oh, it was so good. She's not going to lie. I doubt that. Anybody could, but nobody that cares about reading is going to do. What was the prize? A free book? Because that would have been really funny if it was.
You would get a book, it's or something book related after like $3.
Yeah, like no one's going to lie about that and be like, yeah, you know.
Next year, watch me. Next year, I'll win.
I know, now it's coming. I read 137 books this year, actually.
You were already already wrote
What's that? Oh, it's true. No, you can't. We have it recorded.
Oh.
Sorry. Miss Watkins, if you're listening, Natalie Vestagram, that was 137 quote-unquote books.
I'll read them. She didn't say they couldn't be like children's books.
They have to be at least
150 pages each book. I can do that in a day. I can read like 4 to 5.
All right, FD cosine theta. So, work is related to a force applied. That's the first thing we have to think about. To do work, you have to apply a force, but you also have to do what? Push it over a certain distance. So if I do this, ready? How much work am I doing?
A lot.
None.
Oh, I thought you were pushing it.
I know. I'm not. I mean, can I push? I guess technically it's moving like a millimeter because the board bends, right? But now I'm doing work, right? Isn't that crazy? I'm doing a lot more work doing this than I am trying to push the wall down. But that's because work is a function of distance as well as force. If I asked the question, where am I applying more force? It was clear that in the first example, I was applying more force than the garbage can. I'm barely pushing the garbage can. So work is force times distance cosine theta. Now, theta is the angle between the applied force and the direction of motion. So let's put an object right here. And let's say I'm pushing down on the object like that. Which way would this object move if it were to move? Here's the floor. Which way would it move if it were to move? Thank you. I mean, there's no other answer, right? I hope. Who would say left in this? Nobody. I hope nobody would say left here. So it's going to move to the right. So here's what we do. Take a look, please. Come on. Focus, focus. Extend your lines. Extend your lines. And find that angle between the direction of motion, here it is, and the force itself. There's theta. Okay, that's how you determine what theta is if you're given a value of theta, if you're given a diagram. If it says an object is being pushed at an angle of this many degrees below the horizontal or above the horizontal, or it's being pulled at an angle of 20 degrees. Pulled is the easy one. If it's pulled at an angle of 20, it would look like this. Right? That's the easy one when it's pulled. I'll probably go nice on you on this one. I'll probably go pulled. Okay, if I had something where it's pushed, because when it's pushed, it's hard to understand what theta actually is. Is it being pushed down, or is the object actually taller than you? And you're like trying to, like, imagine you had like a bookshelf. No, that wouldn't make sense. Oh, no, it would. If you had a bookshelf on a dolly, right? Although you probably wouldn't push at the top. You might put a hand here and here, and you push the bookshelf like that. So this force would be up at an angle. This would be down at an angle. You see what I'm saying? So when it's being pushed, it's hard to understand whether the angle is above or below the horizontal. But when you're pulling on something, you're rarely pulling down on an object. You're usually pulling like a sled would be pulled kind of up on an object. Now the idea here is that when you pull at an angle, that pull is in two directions, FPX and FPY. So let's draw them real quick. Here's FPX. And FPX is like the triangle that you would make if you made a right triangle here. All right, make a right triangle there. FPY looks like this. Okay, FPY is in blue there. That's what those values are. And that's what that physically means. Use common sense. If you pull on a sled hard enough, it'll start to lip up off the ground and lift, right? The front lip of it will lift off the ground. Because you're kind of pulling up on it. But it's also going to move this way because you're also pulling to the right. That's what northeast means. It means up and to the right. So as a result, you have forces in multiple directions here. So when you do a free body diagram of this object, that's your beginning. Now we also have to draw other things such as friction, the weight of the object, and the normal force. Okay, and the normal force. This is probably not a good color on here, huh? Let me shut the other light off. You can hopefully see it. The concept, though, here is that if you want to find the work done on an object, you could just simply take the actual force applied, Fp, times the distance it's traveled, times the cosine of that angle right there. What would my units be for work? Anybody remember my units for work? What are my units for work?
Newtons per meter squared.
Not newtons per meter squared. It's joules. It's newtons times meter. Look, force is newtons, distance is meters. Now, recognize that you have really, see this? I'm going to circle it. This F right here and this cosine theta, that's really just FPX. Remember, FPX is always FP cosine theta, and FPY is always FP sine theta. So when you're calculating the work done, you're really just calculating the force in the x direction times the distance, because F cosine theta is what the force in the x direction is anyway. Another thing we should recognize from this, if you know the amount of work being done and you know the mass, you could find the change in velocity because of the work kinetic energy theorem. That's where this is going to most likely be applied. So I might in part A ask you to find the work done on an object. And then in part B, I'd say using the work kinetic energy theorem, determine the final velocity if this object started from rest or started from 1 meter per second or whatever and has a mass of 2 kilograms. So let's look at that. All right, so let's say that the force applied, and this is at an angle of 20 degrees, is 100 newtons, and we'll say that the distance traveled, in this case, was 12 meters. I'm telling you that the mass of the object being pulled is 5 kilograms, and let's say that initially, before this force was applied, it was coasting slightly at a low velocity of 0.5 meters per second. So it was slowly coasting, and then suddenly, so the object is slowly rolling, and you grab the end of it and start pulling with a force of 100 newtons. You keep pulling with a force of 100 newtons for 12 meters. How fast is it going to get? Remember, if you're applying a certain force for 100 newton for a certain distance, if I keep applying this force, it's going to accelerate. F equals ma. Acceleration means increased velocity. So our goal is to find the velocity at the end. So to do this, to step you through this problem, you would start this problem first. Okay, you would first start this problem by saying the work done on the object is FD cosine theta. And that's what I'd probably ask you for in part A. Now, if I directly said find VF, you'd have to just recognize that work also equals the change in kinetic energy. But that'd most likely be part B. So if you find the work done in part A, you could set it equal to delta KE. What's delta KE? What does that mean? Dro?
It's like the final kinetic energy minus the initial.
But Dro, what's kinetic energy? Tell us that.
It's mass times 1/2 mass times velocity squared
Minus.
minus 1/2 mass VI squared.
Good. So that's really what work is. So if you want to, please go ahead, take this right here and set it equal to this right here. FD cosine theta equals 1/2 mvf squared minus 1/2 mvi squared, and just solve for VF. This is a problem where it's going to be messy to solve with all variables. So what should you probably do in a problem like this?
Plug in.
Yeah. This would be a safe bet where I would say, you might want to plug in to make it easier, just because you have FE cosine theta equals 1/2 mvf squared minus 1/2 mvi squared. You'd have to add the 1/2 mvi squared over. I'll run through it like quickly, okay, if you want to, for those that really want to do this analytically, because I know some of you prefer that, so I'll just run through it real quick. Analytically, your answer would be this again. This is the setup. I would start by adding this whole term over to get rid of this. I'd multiply by 2 to get rid of this. I divide by mass and then take the square root. I would go in that order. So I'd FD cosine theta. I'd add the 1/2 MVI squared over, which gets rid of this whole thing. I would multiply by 2 to get rid of this 1/2. And then finally at the very end, so I'd multiply by 2 to get rid of that 1/2. I divide by m to get rid of mass. And then to get rid of the square that's here to get VF by itself, this will leave VF, I would square root this whole thing. Okay, I would not want to do all of that analytically and then plug in, but this would be the answer for VF. Okay, getting rid of this first, then get rid of the 1/2 by multiplying by 2, get rid of m by dividing by m, get rid of the square by square rooting the whole answer. But again, plug in numbers and make it easier on yourself if you feel inclined to do so. This is the easier way if you're confident in your algebraic skills, because there's no numbers to worry about like making mistakes calculating and rounding error. You can plug in right here. But if you find that like sometimes you make mistakes when you're moving stuff around, probably plug in the number earlier.
Wait, how can we cancel out mass?
I didn't cancel out mass. The goal was to solve for VF. So once I get rid of the 1/2 by multiplying by 2, I divided by m to get rid of the m. I didn't cancel it.
There's no initial velocity here, is
There
there?
is, but look, MVI is here, right? This mass is here. If I want to, I could cancel these two, but I can't cancel it here. So it's really not worth going into the effort to take this out of here with the 2. I'd have to distribute the 2, then cancel the m's here. This 2 would cancel with this 1/2, but then there'd be a 2 here. This would still be over m. It's not worth simplifying. When you're going to plug in numbers, don't simplify. Okay? If you want to, if you're solving, if you're taking AP Physics next year and you want to solve algebraically, what you're going to have to do on that, you cancel and simplify wherever you can to see the emphasis of each variable. And you wouldn't even have, the problem would be given without numbers completely. There'd be no numbers involved. What else we got? We have a little bit of time still. That was work, kinetic energy theorem. That was work, or forces at an angle, how you'd break up into FPX and FPY. We have 1 minute actually. Anything theoretical, conceptual? Probably wouldn't be able to get to the whole math problem. There's a double tomorrow. Make sure tonight, spend a little bit of time. You guys don't have any homework, right? I hope you have no homework. Do you have anything?
Speech class.
Oh, that was
All
awesome.
But that's, what is that, memorization?
Yeah.
I mean, try to spend some time tonight. Seriously. Guys, spend time tonight studying math and science. I know you have to class so hard, but math and science, you can come in and ask questions to go over. Whereas, what are you doing honestly in your English or social studies class? Do you just review the topics over and over?
Yeah. It's just like a few questions.
It's like,
Well,
Well, in
find a
US,
class
we don't
that you
really
need
do
help in
anything.
actually. If you don't need help in physics, don't study physics tonight. That's true. If you struggle in English, work on English. But if you're good in physics, don't worry about it. But if you struggle in this class, you should be looking at your notes tonight or something tonight. Okay, whether it's your notes, whether it's your problem sets, look at the actual solutions, go through them. Maybe if you don't understand the steps. Literally reading through solutions helps a lot. It also helps to actually review problems yourself, but just reading through them at the minimum is good. Office hours tomorrow after school. Not today, but tomorrow after school in this room. Or a room up here, whatever.